Welcome to The Explainer. Today, we're going to talk about a machine that's so ridiculously complex and so important that without it, our modern world just wouldn't exist. I'm talking your phone, the internet, AI, all of it. This is the story of the $200 million machine that literally builds our future.
All right, so to really get our heads around this thing, we first have to shrink ourselves down to a scale that is almost impossible to imagine, down into the crazy world that exists inside every single piece of tech you own.
Think about your smartphone, your laptop, or even the giant servers that are powering all this new AI stuff. Deep down, at the very heart of all of them, is a little slice of silicon. And on that slice of silicon is a whole universe that's so small, it almost defies belief. Just how small are we talking? Well, on a single high-end chip, you're looking at over 30 billion transistors. These are the tiny, microscopic on-off switches that are quite literally the building blocks of our entire digital lives.
And when I say tiny, I really mean it. The smallest parts on these transistors are only about 10 nanometers wide. To put that into perspective for you, that's like lining up just 45 silicon atoms side by side. It's a scale that's it's hard to even wrap your brain around.
So yeah, this leads to the big question, right? How in the world do you actually build something so complex, so unbelievably small, and do it millions of times, perfectly? I mean, it sounds completely impossible. But there is a way.
The answer is a process called photolithography, and it's all done by a machine that's, well, it's less like a photocopier and a lot more like something straight out of science fiction. So the easiest way to think about these amazing machines is as nanoscale photocopiers. Except instead of using ink on paper, they use light to print these incredibly complex circuit designs onto disks of pure silicon. But here's where that whole photocopier analogy kind of breaks down pretty fast. See, to make things that are smaller than the wavelength of visible light itself, well, a regular photocopier or even a normal light source is totally useless. You need a completely different kind of machine that uses a completely different and very special kind of light.
Okay, here's a simple way to think about it. Imagine light is like the tip of a marker. If you want to draw a really thick line, you use a big, fat marker, right? But if you want to draw incredibly fine, thin lines, you need a marker with an extremely fine tip. Well, for drawing at the nanometer scale, that ultra-fine tip is a special type of light called extreme ultraviolet, or EUV.
All right, so let's pop the hood on this $200 million marvel and see exactly how it creates and controls this impossibly thin light.
You can basically break this machine down into 5 main parts, and they all have to work together perfectly. But everything, and I mean everything, starts with this enormous challenge of creating a kind of light that just doesn't naturally exist here on Earth.
And yeah, this really is the heart of the problem, isn't it? How do you generate powerful, stable, extreme ultraviolet light whenever you want it, inside a factory? This isn't something you can just, flip a switch for. The solution is, it's just wild. It's an incredible display of physics. First, the machine shoots out a tiny, microscopic droplet of pure, molten tin. A low-power laser zaps it, flattening it into a perfect little pancake. And then, bam! A second, insanely powerful laser blast just vaporizes that tin pancake, creating a super hot plasma that glows with the exact EUV light they need.
And get this whole laser and tin droplet dance, it happens 50,000 times, every single second. The speed is just absolutely mind-blowing.
Now, this EUV light is super powerful, but it's also really finicky. It gets absorbed by pretty much everything, even the air. So the entire journey for the light has to happen inside a perfect vacuum. And you can't use regular glass lenses. No, you have to use a series of mirrors that are so perfectly smooth that any bump or imperfection is smaller than a single atom. We're talking about the smoothest surfaces ever created by human hands, period.
Okay, so let's zoom back out for a second and see how this amazing machine fits into the much bigger picture, the months-long process of building a microchip, one tiny layer at a time. So, the whole process is basically a super high-tech version of stenciling. First, they coat a silicon wafer with a light-sensitive material. That's your paint. Then, the EUV machine acts as the stencil, tracing an intricate pattern with light. You wash away the parts that got hit with the light, and then you either etch away material or add a new layer. And then, you just do it all over again. And they just repeat this loop over and over and over again. A single complex chip
like a new graphics card, needs this cycle to be repeated maybe 80 times. It's meticulously building up this three-dimensional maze of transistors and wires, layer by microscopic layer.
This whole journey, from a shiny, blank wafer of silicon to a finished set of chips that are ready to be sent out into the world, we're talking about 4 months. It's a marathon of unbelievable, painstaking precision.
And if you really want to wrap your head around the insane level of detail this machine is capable of, get this. The amount of information it patterns onto a single chip is equivalent to the text of the entire Harry Potter series, every book Stephen King has ever written, and all of Wikipedia. All of that info printed nanometers at a time, it's just staggering.
So here's the bottom line. It is absolutely no exaggeration to say that this one machine is the hidden engine driving our entire modern world. From the smartphone in your pocket, to the advanced medical gear in hospitals, to the computers guiding rockets into space, pretty much every piece of advanced technology that you rely on every day is only possible because of this one truly extraordinary machine.